Hey everyone, welcome to This Explainer. Today we're jumping right into one of the absolute most thrilling ideas in modern science. For decades, scientists have been hunting for the missing pieces of our universe, specifically dark matter and dark energy. But what if we've been looking at the problem slightly wrong? Today, we're going to use a strict, structured visual approach to break down a fascinating, highly testable new hypothesis that might honestly change how we see reality itself.
So picture this. The standard models tell us that dark matter and dark energy are missing invisible particles, right? Or maybe mysterious forces. And we've spent billions, literally billions of dollars building massive underground detectors and launching these incredible space telescopes just trying to find them. But what if we'd been looking for the wrong kind of clue entirely? What if the universe isn't hiding invisible objects, but is actually operating on a hidden set of instructions? It's a pretty wild thought, that we might be spending all this time and money looking for physical particles when the answer could just be structural math.
Here's our roadmap for today's explainer. First, the missing universe problem. Second, the TDH hypothesis. Third, testing the structure. Fourth, falsification rules. And finally, the real-world impact.
Section 1. The missing universe problem. Structural divergence.
Let's start with exactly where we are right now in physics, and why our current model of the cosmos is kind of acting like a physical structure under extreme stress. Think of our current understanding of the universe, the standard model, like a giant, incredibly sturdy bridge, and it works amazingly well. It safely carries us over the waters of confusion, explaining massive things like how stars burn and the background radiation left over from the Big Bang. But right now, this bridge has accumulated what researchers call structural divergence. In everyday 8th grade terms, that basically just means unexplained stress. The math simply doesn't quite match what we're actually seeing through our telescopes.
And we've got these major unresolved pressure points. First off, despite some truly incredible experiments, we still haven't found a single dark matter particle. Not one. Second, we don't actually know the physical mechanism that makes dark energy push the universe apart. Plus, there's this thing called the Hubble tension, which basically means the universe seems to be expanding at totally different speeds depending on how we measure it. All these stress points, they're telling us something big is missing.
Section 2. The THD hypothesis. Informational geometry.
Now, when a bridge is under this much stress, and patching it up just isn't working anymore, you need to look at a totally new structural approach. And this is exactly where researcher, inventor, and author Kevin L. Brown comes in with a fascinating new framework. It's called triune harmonic dynamics, or THD for short. Brown suggests that we might actually be leaving out a massive physical variable. He proposes that information itself should be treated as a physically real building block of the universe, just as important and just as real as gravity or light.
He calls this concept informational geometry. So instead of imagining invisible, heavy particles weighing down galaxies to keep them from flying apart, I want you to imagine an invisible geometric blueprint. This blueprint is an actual physical property of the universe that guides how matter clumps together, how galaxies form, and exactly how they spin. The information literally acts as a structural scaffolding.
For a really long time, physics has run on a two-part system: matter and energy plus space-time. But the THD view shifts us to a three-part universe. It adds information directly into the mix. If this holds up, dark matter and dark energy aren't just invisible substances we haven't found yet. They're actually the signs of this hidden informational geometry doing its invisible work.
Section 3. Testing the structure. Observable confirmations.
Now, any scientific hypothesis is only as good as our ability to actually test it, right? You can't just invent an invisible blueprint and expect people to believe it. Since we can't see this informational geometry directly with our own eyes, scientists have to look for the fingerprints it leaves behind. And Brown's research lays out exactly how to do this using validation tests. Basically, scientists map the shapes of galaxies. They measure the massive cosmic web that connects clusters of galaxies, and then they calculate what's called a coherence index. Think of this as a mathematical score of just how organized the structure really is.
When we run these tests, we're looking for confirmation signals. For example, if we take our current math for how a galaxy rotates and it doesn't quite work, we add in that information index score. If the math suddenly predicts the galaxy's rotation perfectly, boom, that's a confirmation signal. The same goes for the cosmic web. If the strange gravitational poles we observe perfectly match the informational structure rather than just the visible matter, the hypothesis gains massive, testable support.
Section 4. Falsification rules. Breaking the hypothesis.
In science, proving you're right is really only half the battle. You also have to explicitly state how someone could prove you wrong. And Kevin L. Brown's hypothesis is highly rigorous here, because it comes with built-in self-destruct buttons. So how do you break this idea? Well, if an underground lab finally catches a real dark matter particle tomorrow, this hypothesis fails. If this informational model cannot perfectly match the ancient light from the Big Bang, the cosmic microwave background, it fails. If it can't explain massive galaxy collisions like the famous bullet cluster, it gets tossed out entirely.
But here is the absolutely most important falsification rule. Zero. Zero arbitrary tweaking is allowed. In a lot of complex science, if an equation doesn't fit the data, researchers might subtly tweak a number after the fact to, make it look right. This model explicitly forbids that. The math has to be locked in advance. If researchers test a new set of galaxies and the math doesn't naturally predict what they see without cheating, the hypothesis is entirely falsified. No takebacks.
Section 5. Real-world impact. Beyond astrophysics.
Now, if this strict testing actually holds up, the results go way, way beyond just looking at the stars. The logic here is really about finding hidden structural pressure before a system completely breaks. If information acts as a real scaffolding in space, we can transfer that exact same mathematical logic to other huge, everyday systems. We can look for hidden structural pressure in human biology, in complex financial markets, in massive power grids, and even in advanced engineering. Hidden structure governs visible outcomes everywhere.
Ultimately, this could completely transform how we handle crises across the board. Instead of just making blind guesses about when a market will crash or a system will fail, institutions could use these models to spot when their systems are groaning under invisible stress. They'd be able to see the model breaking down in the math long before the actual crisis hits the front page. That's a real game changer.
It's a radical, brilliant shift, really, moving from searching for missing puzzle pieces to realizing the table we're building the puzzle on has its own hidden geometry. And it leaves us with a profound thought to wrap up on. If the entire cosmos is fundamentally built on an unseen, testable informational blueprint, how much of our everyday reality is just waiting to be decoded? Thanks for exploring this with me today, and keep asking the big questions.